So hello everyone. First of all, I would like to thank the organizer for giving to me the opportunity to present my works. So I'm a first year PhD at the Institut Charles Gard in Montpellier. And today I will present my work based on the self-energy as a functional of the density matrix via an embedding approach. So the aim of this project is to determine the electronic structure and also to deal with the correlation. So quickly, what is correlation? Correlation is when you consider the electronic interaction. Here represented the ground state energy of a small molecule, which is H2, as a functional of the interatomic distance. In the blue line, you can see the calculation where the correlation is treated as an average, R, and where in black, you can find a calculation where the correlation is treated exactly. For this small system, the correlation energy, which is a gap between both calculations, is nearly equal to 1.5 eV for a small system where the correlation is not preponderant. However, considering exactly the correlation, meaning that the numerical cost become very expensive, and essentially due to the exponential growth of the basis set with the number of orbitals. So in order to define an approximation of this correlation energy, several methods has been developed. So as it was well explained yesterday by Lucia, we have a competition between the complexity of the variables and the complexity of the functional. For the density functional theory formalism, for example, where the fundamental variable is the density, you can obtain the correlation energy as a functional of the density. However, even if the numerical cost is quite cheap, you cannot access lots of observables. However, a natural extension of the density as a variable is by using the reduced density matrix. However, the representability of this density matrix is not well known, especially the very representability, and functional are quite complicated to construct. In order to obtain a dynamic description of the electronic structure to obtain spectroscopic properties, for example, a dynamic variable is necessary, which is the case for the green functions, where the dynamic mean field theory or the JW approximation, for example, use this green function to obtain a dynamic description of the electronic structure. But despite the complexity are quite simple, both approaches are numerically very numerically expensive. So in order to mine this gap, we will try to have a dynamic description of the electronic structure as using the green function for our variable fundamental or of your fundamental variables. Sorry. However, we'll try to find a way to construct a functional which is quite simple by, as it was already done, using an embedding scheme. However, it remains a problem that was greatly explained yesterday by Lucia and Eric, is that we don't know the domain of representability or the shape of the self-energy. So for that, we investigate what it has done before, starting with the DFT formalism. A univoc relation was found between the external potential and the density for the DFT and the density matrix for the reduced DMFT, using the Concham or the Gilbert theorem. Therefore, with the self-energy functional theory developed by Potov, reciprocal was found with the self-energy and the external potential. In our case, we will try to close this loop by having both advantages of the density matrix and the self-energy, by consider the self-energy as a functional of the density matrix, as it was done, for example, with the Hartree-Fock approximation or the Hubbard one, where the self-energy is a function of the density of the density matrix. Then, in this case, we can obtain a dynamic description of the electronic structure but by using the density matrix where the variational domain is well known, we can construct such self-energy without considering the domain of representability. However, it is possible to find a systematic way to construct such functional. So in the first, for that, I will present an embedding scheme to obtain such a self-energy as a functional of the density matrix. So starting with the density matrix, we choose a site as a target site, which is here is in red, which is called 0. And by applying on the density matrix the Householder unitary transformation, you transform your density matrix into a density matrix where all the kinetic energy is relocalized into a small cluster where the target set will remain exactly the same. Therefore, the cluster does not interact with an environmental path. So, with this embedding scheme, we can extract on-site property using exact diagonalization, and with the self-consistent condition, which is exactly the same as the DMFT self-consistent condition, the self-energy of the target site in the cluster become equal to the target site self-energy, and it is reintroduced through the Dyson equation. After that, we can determine the self-energy of the system self-consistently. However, despite this embedding looks very attractive, some approximations are made. So starting from the non-correlated cases where u equal to 0, by applying the Householder, which is also the Schmidt decomposition for the non-correlated case, you obtain a reduced size cluster, which does not interact with the bus and where the number of electrons within the cluster is fixed. However, by introducing correlation, the Householder transformation, we will obtain a cluster, but which interact weakly with a bath, and where the number of electrons is not well fixed. So in the first approximation, we will neglect this interaction between the small cluster and the bath, and we will fix the number of electrons for the cluster. So now I will present my very first result that I have obtained. So here it is represented on my numerical result on the one-dimensional U-bar at thermodynamic limits for half filling, where I computed the total energy per site in function of U divided by U plus 40. So it means that for 0, you have the non-correlated case, for 1, the atomic limits, and for 0.5, which correspond to the non-interacting bandwidth, which is equal to 4 times T. In blue, you have my results obtained. In red, the result obtained by the two-side DMFT made by Potov, which is one of the cheapest DMFT, but also the most efficient for two sites. Then in green, you have the U-bar 1 approximation. And finally, in black, the Bethe solution, which are exact. So as you can see, our results are very close of those found with Potov. And then our results are very close to the Bethe limit for the non-correlated case. However, we find a mod U-bar transition similarly as Potov for nearly the same value of a critical U, which correspond to a mod U-bar transition, and where the solution are now equivalent of the U-bar 1 approximation. So for the low correlated limit, we found a better result than the U-bar 1 approximation, which expresses the self-energy as a functional of the density only, and not on the density matrix. Now, to conclude with our method, we find a systematic way to construct the self-energy as a functional of the density matrix. And then we compare our result with Potov, and we found a very close result for only two sites. However, our results are still better than those found with the U-bar 1 approximation. But a main advantage is that we can easily control the error by increasing the size of the cluster easily with the thanks to the Householder transformation. So what's next? We will try to find a dynamical way to our embedding scheme, because we deal with dynamic variables. So it would be pertinent in this case to find a dynamic way to obtain an embedding scheme for different value of omega. Then, by increasing the size of the cluster, we want to find a way to deal with the non-local self-energy, which remain non-trivial and must be greatly increase our method. Thank you for your attention.
Okay, thanks, Quentin. Okay, so we have time for a few questions again. So I have, okay, I have Kozik and then Emmanuel Fromager. You can ask a question first. Ah, sorry. Okay, then Manu, you can ask a question.
Yeah. Okay. Yes. Sorry. So okay. So I'm asking a question because this is the first time I see these results. So thank you, Quentin. So your method has problems in the very strong correlation regime, and I was wondering. So what about the occupation of your impurity? I mean, do you check that it's still? I mean, because in the mean field, when you start your calculation, you have the right occupation. I mean, what you call the density. But when you solve the Dyson equation, then if you don't do anything, if you don't touch anything, I guess you will get a bad occupation. So usually people in embedding techniques add a chemical potential to restore the proper occupation.
Yes,
Could
exactly.
that be the reason for this bad performance of the method? Yeah.
Exactly. Yes. So in our cases,
correct for this, you would improve on your results, I guess.
So the chemical potential of the self-energy is well fit to respect the number of electrons on the site. So
okay.
Yes, in this case, the number of the electron is equal to 1 for the half-filling
okay.
homogeneous case by considering a chemical potential.
I see. Okay. Okay. Thank you.
Thank you.
Any other questions? So just I was wondering, because now you have your self-energy in terms of the density matrix. Is there any relation with, or can it be used for, is there any relation with this Kadanoff-by ansatz that Robert was speaking about, in which at the end you can express essentially your self-energy in terms of density matrix as well. So then you can close your equation of motion for the density matrix, or can be used in that case.
I think I didn't well understood your questions.
So now you have a self-energy, which is a function of the one-body density matrix.
Yes, exactly.
Can this be exploited in a non-equilibrium Green's function in which you solve just for the one-body density matrix?
Yes, for sure. I think that we found a way to express this self-energy, which was not fully explored before, despite the Hartree-Fock self-energy, for example. So there is maybe a way to open so this way of finding the self-energy of the functional of this density matrix, and this work is in progress. So there to find the univoc relation between the density matrix and the self-energy. Did I well answer to your question or not?
Yeah, yeah. Okay, I have other two questions. One from Jean-Paul Brun and then Simon. Jean-Paul?
Yeah, when you separate your system, so do you have to be consistent with some let's say entanglement entropy area law, or do you have to preserve some stuff when approximating the bath, or?
Yes, for the approximation in the first way, interaction are completely neglected because they are very weak. But a less trivial problem is for the number of electrons within the cluster. In fact, it is fixed with the U equals 0, which is exact. With this condition, we treat our correlated system exactly as the same as if it is not correlated.
Okay.
Okay.
Thanks.
So in the next way, we can maybe approximate here our interaction with a mean field within a mean field approach, or in the ground canonical approach, for example, to treat different ways to obtain such interaction within the cluster.
Mm-hmm. Okay, then maybe we take a last question. There's a question by Simon.
Mm-hmm.
Yeah, so I was wondering that if I have the self energy as a function of the Green's function, then in both of these I have the same amount of information, so to speak. So I have the same degree of dynamics. So I have 2 times, or if I do Fourier transform, I have 1 frequency. Mm-hmm. If I have the density functional theory, then I have 1 time, or no time. Whereas here it seems like there is less dynamics in the density matrix than in the self-energy. So how do you get that extra dynamics in the self-energy that you don't seem to have in the density matrix?
Okay. I guess I see. In fact, with this embedding scheme, so you apply the interior transformation on the density matrix. After that, your density matrix is mapped into a U-bar system, and you extract the self-energy of this system. If you consider the 2 sites cluster, your self-energy is the same as the dimer, where the parameters of this dimer are expressed with respect to this Householder transformation. This transformation is just a way to relocalize the kinetic energy within a small system. When your system is now defined exactly with the Householder vector, you can extract the dynamic response from a kind of clusterized system. But I think that for the half filling and in the homogeneous case, it is possible to define explicitly for a 2-site cluster the self-energy as a functional of the density matrix with respect to the particle electron symmetry, particle hole symmetry.
So you're saying the embedding method is important, is an important ingredient in this mapping from gamma to sigma?
Yes, it is. It is important because if you consider the DMET, which is also used a different embedding scheme, here your transformation is applied on the density matrix, which is quite important for this representation. And this is why it is also possible to express the self-energy as a function of the density matrix.
Okay, thank you.